Titanium matches the strength of steel, but it is 40% lighter. Compared to aluminum, it offers nearly twice the strength. That ratio makes it vital for extreme environments. During supersonic flight, friction against the air creates temperatures that would compromise standard aerospace alloys. The SR-71 Blackbird, seen here, relied on a titanium skin to maintain structural integrity under that intense heat. It also exhibits a unique biological harmony. Unlike most metals, living human bone can fuse directly to its surface without triggering an immune rejection or inflammation. Solid where others melt, lighter than steel, integrating with living bone, a combination of traits found in no other element. Despite its value, the element is not scarce. It is common in river sand and mountain ranges, and as this view of the lunar surface suggests, it is distributed throughout the solar system. Yet, for more than 100 years after its discovery, the scientific community could not extract a single usable sample of the pure metal. Standard metallurgy fails here. For thousands of years, humans have smelted iron by simply heating ore with carbon, but applying that same logic to titanium yields nothing but waste. The problem is the metal's chemical appetite. When heated in normal air, it aggressively absorbs oxygen, nitrogen, and carbon. Instead of a strong ingot, the metal shatters into a dark, brittle powder. Nature bonded this metal to the earth with a chemistry that traditional smelting, using mere fire and carbon, cannot overcome. Releasing the metal requires a multi-stage chemical workaround to bypass its bond with oxygen. First, the raw ore is processed with chlorine gas at high temperatures. This reaction severs the titanium's connection to oxygen. This creates titanium chloride, a transparent, fuming liquid that is highly reactive and must be handled with extreme care. This liquid is then injected into a sealed vacuum reactor and mixed with molten magnesium, a substance that is even more reactive than the titanium itself. As shown in this molecular visualization, the magnesium strips the chlorine atoms away to form its own bond. This leaves behind a porous, pure mass known as titanium sponge. This violent, indirect molecular exchange is the only reliable way to force the metal into a pure, usable state. At this stage, the titanium sponge is still highly vulnerable. If it is melted in open air, it will immediately reabsorb oxygen and become ruined. To create a solid ingot, the sponge must be crushed and pressed into blocks, then melted inside an absolute vacuum or a chamber filled with inert gas. Within this void, an intense heat source, such as a focused electron beam, fuses the metal into a smooth, glowing liquid pool. Unlike steel, which is produced in a continuous, high-volume flow, titanium is processed in slow, energy-intensive batches. The high market price of titanium reflects the sheer volume of electricity and vacuum-grade engineering required to overcome its reactive nature, rather than a lack of raw ore. There is a central irony in this process. The same chemical appetite for oxygen that makes extraction so difficult is actually the source of the metal's durability. When pure titanium touches the atmosphere, it pulls oxygen to its surface, forming an invisible oxide armor. When scratched, oxygen particles instantly patch the breach. This self-healing property lets it survive decades in salt water or the human body. Most mined titanium never reaches this metallic state. Instead, it is left bonded with oxygen to create titanium dioxide, a stable, brilliant white powder used to pigment everything from house paint to toothpaste. This stable pigment stands in contrast to pure titanium dust, which is volatile and ignites with a blinding white flame if exposed to a spark. The same aggressive chemistry that kept titanium out of human reach for a century is exactly what now protects it in the depths of the ocean and the heat of the sky. The current engineering race is focused on developing a continuous, low-cost extraction method that can replace the complex magnesium-based process. If successful, the cost could drop to the level of aluminum. The advanced materials currently reserved for jet engine turbine blades could eventually become standard in everyday cars and construction. Overcoming the high cost of extraction will transform titanium from an aerospace specialty into a foundational material for our daily infrastructure.